Hello, my name is Samson Hagos. This work is done primarily by the WASM team at PNNL in collaboration with Minsop and at Lawrence Livermore and Charlotte Demott at CSU. It's aimed at understanding the origins of the biases in tropical precipitation climatology in CMIP6 simulations. If you look at the precipitation climatology in CMIP6 models in comparison with observations, you see this bias with excess precipitation over the oceans, especially off the equator, that we refer to as double ITCZ, and dry bias over land. So in this study, we aim to examine the origins of these biases using analysis of moisture, energy, and mass budgets. Our theoretical analysis indicates that these biases are related to the representation of precipitation and its relationship to precipitable water. Specifically, we derive an equation that relates precipitation with a normalized form of precipitable water and evaporation. So what this equation indicates is that the statistics of precipitable water and how it relates to a given critical value represents at what regime the model is operating. If that precipitable water normalized form is much less than the critical value, then precipitation is operating in evaporation controlled regime. So that's where you find that double ITCZ kind of feature, because precipitation will be excess over higher evaporation regions. On the other hand, if the precipitable water is greater than the critical value and approach the asymptotic limit, then precipitation approaches infinity. That would be the regime that's primarily controlled by precipitable water. So this is a theoretical analysis. When you look at the behavior of the models with high and low critical normalized value, you see that this behavior explains much of the biases in these models. The models that have high critical normalized precipitable water tend to contribute more than their share to the model biases. So that brings us to the question, what is this critical normalized precipitable water? If we consider the familiar relationship between precipitable water and precipitation, it can be derived from the moisture budget equation as we show here in an idealized form. So the key parameters that define this structure are the PW0 and PW limit. And then critical normalized precipitable water is defined from them. So the PW0 is basically the precipitable water value at which moisture convergence changes sign. And the PW limit represents the evolution of the vertical structure of moisture convergence with increasing precipitation. Therefore, these quantities are basically telling us about the relationship between the depths of the clouds and the production of precipitation. So this behavior represents the relationship between precipitation and precipitable water, and also ultimately the climatology of tropical precipitation. In terms of research needs and opportunities, say in the next 3 to 5 years, I think the community could challenge climate models in their representation of cloud populations, all the way from isolated shallow clouds to MCSs, along with the environmental conditions, their depths, and their precipitation production. What it would allow us to do is that the representation and the prediction of the frequency of extremes would lay on a solid foundation of cloud populations as opposed to just bulk representation of clouds as they are parameterized. In long term, say next 5 to 10 years, we need to systematically characterize the impacts of biases like this and others on Earth system predictability inferred from these models and the skills of these models in prediction. This is challenging but important, since ultimately our confidence in these models hinges on the reduction and characterization of these biases and their potential effects on predictability as well as in the skill. Thank you.